Hello and welcome. For this project, our group decided to do an egg drop experiment, and we chose two different size parachutes, a medium and a large, as well as a control, to test for terminal velocity to see if terminal velocity would increase or decrease as the cross sections of the parachutes got larger. Terminal velocity can be defined as the steady, unchanging speed at which drag exactly counterbalances an applied force. We are looking at terminal velocity instead of picking random points to look at velocity, because terminal velocity tells us the maximum speed that an object, a falling object, can get to. Alright, let's switch gears and look at the equations that we will be using.
Using Newton's second law of motion, the sum of the forces, or the net force, is equal to mass times acceleration. We are looking at the forces acting on a falling object in motion, therefore only drag and weight are considered. Acceleration is set equal to 0 when at terminal velocity, since terminal velocity doesn't change at this point. Therefore, the equation to solve for terminal velocity is the square root of 2 times the mass of the egg inside the contraption times the gravitational field divided by air density multiplied by the drag coefficient and the cross-sectional area of the parachute.
A egg was placed in a contraption and was dropped from the second floor of the Sands building at ASU West. When you look at the position versus time graph, the trace of the object freefalling can be seen, and it shows the position over time from the moment it was dropped from off the second story. After adding the linear line fit, the slope of the velocity versus time graph was observed to be 9.38 meters per second squared, which is close to the freefalling acceleration of 9.8 meters second squared. According to the graph, terminal velocity was not reached, but through calculating the control's terminal velocity, we get a value that was not 0. To get a feeling of what the expected terminal velocity will be here, we calculated using the equation from Newton's second law as mentioned earlier. We predicted that the terminal velocity will be greater than the fastest speeds that we observed with the parachute added. After inputting the values into the equation, we get a calculated terminal velocity about 18 meters per second. This is what we expected. This explains why laboratory experiments don't include freefall calculations for terminal velocity.
For this trial, an egg was placed in a contraption that had a trash bag attached as a parachute and was dropped off from the same height. After adding a natural exponent fit, the terminal velocity was observed to be 4.41 meters per second. This was determined by eyeballing the points in which the natural exponent line of best fits levels off. Using the equation mentioned earlier to calculate the expected terminal velocity for the medium parachute, we got a calculated terminal velocity of approximately 1.9 meters per second squared. Once again, the values for mass, gravitational field, and air density are the same as the last calculation. The drag coefficient is 0.8, which is the drag coefficient for the cylindrical shape of the trash bag when dropped. Due to the addition of a parachute, area is now calculated as pi times radius squared for the cross-section area of the trash bag, plus 0.0025 meters squared. Comparing the terminal velocity determined from the video analyst graph versus the calculated value, we're off by a factor of 2. The graph matches the theoretical prediction that as an object approaches terminal velocity, its acceleration decreases. We calculated percent discrepancy of approximately 135%.
For the last trial, an egg was placed in a contraption that had a tar parachute. It's worth mentioning here that the points to track the parachute falling started a little later in the video, not right at the top of the second story. This is because the experimenters were still holding the large tar parachute and couldn't reach high enough to get the tracking points of the contraption to be directly where the other trials were dropped. Like all the trials, the points began to be plotted when the experimenters fully had their hands off the parachute. When observing the velocity versus time graph, we see that it starts to level off and oscillate at approximately 2.5 meters per second. The oscillation in the data point is mainly due to this being a real-life experiment that includes possible variables like wind gusts and rocking. This is why the points vary between 2 and 3 in the velocity versus time graph. Using the equation mentioned earlier to calculate the expected terminal velocity for the large parachute, we got a calculated terminal velocity of 0.839 meters per second after plugging in the values. For full details, see the paper. After calculating expected terminal velocity, we calculated a percent discrepancy of approximately 198%.
Through the completion of this experiment, we found that the terminal velocity actually decreases as the cross-section area of the parachute increases. While there is a significantly high percent discrepancy as shown in the calculations for all the trials, that can be explained through the complexity of drag experiments in real life. When we get to terminal velocity, drag and weight force counterbalance one another. For a given speed, drag force is small. It would take a big speed for drag force to get big when the cross-section area is small. As the cross-section area is small, terminal velocity is big. As the cross-section area gets bigger, terminal velocity gets smaller because there's more room for the drag air to take up in the parachute. Drag experiments are typically complicated to conduct in real life since it's a complicated phenomenon on its own. Factors like wind and the object rocking back and forth while falling could lead to variation in the observed terminal velocity as well as high percent discrepancies.